Hello and welcome back to Calculus 1. The first lecture, right, of actual calculus. All we did so far was pre-calc review. So the first lecture of calculus, the lecture on limits. As I said last week, calculus consists of three major concepts. One is on limits, one is on derivatives, and one is on integrals. And we are going to talk about all three in Calculus 1. So now, first we have to deal with the limit, which will be used to define later in differentiation, and also to define integration in some sense, the Riemann integral and so on. So these limits are important. Now, unfortunately, the definition, the way this is set up in the book, is the definition for this is all the way at the end, in chapter 2.7, section 2.7. So we'll be actually working with the limits first, and then we'll see at the end what they are, which is historically what actually happened. People used them for about 200 years, and then they finally defined the precise definition of a limit. So let's first just write a quick notation for the limit. So notation for the limit is going to be like this. Limit as, let's say, x approaches some number a, that would be like, let's say, x goes to 3 or something like that, of whatever function goes there, is going to give you either a limit, which is a number, so I'll call that finite limit, or it's going to give you one of the infinities, that's infinite limit, or it's going to give you does not exist. So this is the notation, and these are the things that you can expect as answers. So you can have that the limit of x squared as x goes to 3 is equal to 9, right? So that will be a number. Or you can have limit e to the x as x goes to infinity, you get infinity, and then you can get 1 over x as x goes to 0 to be does not exist. So you can have all of these answers possible. So that's technically the notation. Now also observe that you have this part here, which is a function, and this is why it was so important for us to review the definition of a function. You can't take the limit of a circle as an equation as it is. You have to be creative and figure out exactly what you are talking about. So there is that part that you have to have a function, and then also there is this part here, which is showing the motion in the whole thing, because x approaches a value. So this is not x equals 3. This is x goes to 3. And you can go to 3 from two different directions, right? You can, to 3, you can come in from number 2, or you can come in from number 4. So you can come in from left or right. So you have those three aspects. Motion, it has to be a function, and you have one of these three answers. So that's the first thing. Now the next thing that it's important to understand here is that the limit essentially is going to compute the y value of the function, but it's a much more powerful calculation than what you know from pre-calc, where you just plug in a number. So if I am to write that, let's say I'm observing just x squared as a function. If I am to write f of 2, then I will have to say 2 squared is equal to 4, and I am done. On the other hand, limit of x squared as x goes to 2 is also 4. Right? So you get the same result. But we are going to see later that for certain cases, limit will be able to offer you more in terms of these y answers than pre-calc when you are just allowed to plug in one point. So there is going to be a difference. But essentially, if you want the most basic idea of what the limit is, you can go by saying, oh, it just computes the y value. Because it does, right? But it computes it in a different way than what you're used to, and it's much more powerful than what you know so far. So that's the first idea, and now we're going to take a look which way the limit is different than your pre-calculus calculation. So this is like you have I don't know, a match or boxing match or whatever, and you have the blue corner and red corner, and one is in the one and the other one is right. Which one is going to win? Well, clearly limit, all right, because it's a heavier category. So for pre-calculus, you know that you can draw the graph, and you can go and find your 2, 4, right, the answer 4. And the way you compute is, you have this curve, right, already given. You go to 2, you go up until you hit the line, and that bounces right into the y-axis, and you compute that y is equal to 4. And then you can call this point 2, 4 if you want to. But again, please look at the screen. This is what's happening. From 2, the motion goes up and then bounces over. And that's how you get that the answer is 4. So it was a single point. It was a single point going up and bouncing off of the line into 4. Now, the interesting concept here is that if this point here, 2, 4, was excluded from the graph, for whatever reason, was excluded from the graph, if you are to go with the vertical line from 2 up, it will pierce right through that hole, and it would go forever up. It would never bounce back to the y-axis, and you will never be able to compute 4. So if that point was missing there in a graph, and all other points were there, but just that one was missing, you would not be able to compute f of 2. Because the line would just pass through the empty point, and it will go forever up, and it will never bounce off to hit the y and tell you, oh, it's 4. Limit can compute those situations when you have such holes. And that's why limit is more powerful. But before we get to see how's that done, let's first discuss the idea of the limit, the way the limit computes. And then after that you can we can take a look at weird cases where the limit is really valuable. So what I'm going to do now is I'm going to draw this a little bit wider so that we can see it easy. I'm going to pick this to be 4 and this to be 2 so that we can see what's happening here. All right. What is the way that limit computes things? Well, you have this thing here which says that x approaches a. X is a variable on the x-axis which is moving left and right, right? And you have the arrow, which is motion. So what I'm going to do now is I'm going to draw that motion on the x-axis, right? Now, if you carefully observe, any x point, that x is going to travel, right? That point is going to travel on the curve as the x is, I don't know, x is 1, x is 1.1, x is 1.2, 1.3, 1.4, 1.447, right? So you can pick any values. As the x progresses from left towards number 2, the y values march up, in this case, up the x curve, which means that they are also marching up. So there is a motion towards 2 which triggers the motion up the curve, which triggers the motion up the y-axis. So all of these are happening simultaneously, right? So you pick one point, right? You pick this point, it goes there, it bounces here. You pick that point, it goes there, it bounces there. And you can see clearly the way it progresses, right? As the x values go towards 2, the points along the curve march upwards, and the y values march upwards. So where is it going to stop, this type of a march? Well, if we are to go up, right? If we are to go up, it will go all these points, and then you eventually reach 2, and you can't approach 2 anymore from the left, so you have to stop, right? So you would get to number 4, and because you can't approach 2 anymore from the left, you can't pass 4 on the y-axis. But then you also realize that you can approach 2 from the right, which is the blue one. Now the blue one will go down the line towards 4, which are all the blue points going this way. And as you can see, the red goes from the left, the blue goes from the right. They collide at 2, but also the red and the blue arrows on the y at the same time collide at 4. So what is this limit actually doing? I mean, we got the same answer, right? What limit did is limit computed infinitely many points around 2, computed the y values for infinitely many x points around 2, and looked at the trend of those points. And the trend of those points said, we're all going to 4, from both ways. So we actually never ever computed at 2. We computed at all of the infinity of the points around 2, and we never computed at 2. And that is what makes this concept so powerful. Because if that point was not there, right, the 2, 4 point, no one cares, because we never used it to compute anything. Precalculus computes at that point. And if that point is not there, Precalc has a problem. I can't compute function value if the function value is not there. But the limit says I don't care about that one point. I can compute infinitely many points around that point and just infer it's that point. And since infinity of the points is much more than the one single point, obviously it has to give us the good answer, right? So as you approach from the left, for this particular graph, the points march up, which is the march of the y values up. The blue points from the right will go this way. I see we have the sync issues because it keeps deleting stuff. It goes down, it will go down, and they will meet here. We are going to see this in a definition clearly with some epsilons, delta, and some tubes and squeezing and so on. It will make even more sense once you see the full definition. But the important part is to understand that we are computing infinitely many points around 2, their y values, right? And the y values will march towards 4. Now the motion is captured by you simply picking points that are approaching the value that you want. If you are supposed to approach, let's say you're supposed to approach 2. You will approach 2 as 1, 1.1, 1.2, 1.3, 1.4. You can approach it even better. You can say 1.9, 1.99, 1.999, 1.99999, right? So you can approach it that way. There are many ways in which you can approach. So we'll be going down this way. We'll be going up this way. So hopefully this thing doesn't get to be really annoying, deleting everything. So now what you see on this graph, I am going to put in the chart of values, table of values, whatever. So we want to know what is happening at 2. What I'm going to do is I'm going to, let's say, use 3 numbers on each side. I'm going to say 1.9, 1.99, and 1.999, because you can see that it's always closer, right? You have $1.90 and $1.99 and then $1.99 and 9/10 cents, like when you're pumping gas. Do you know that 9/10 is 9/10 cents? It took me a very long time to figure it out when I moved to US. And I asked every time, because, you know, I stopped by and I asked the guy, what is that? Because I didn't know. And most of the people didn't know what to tell me what it is. And then finally I found out what it is. And I asked for change right away. Just to be annoying. It's like, why do you put that there? Why? You can't give me change. I mean, come on. Right? Anyway. So you can see that we are getting closer to number 2. From the other side, 2.1, 2.01, and 2.001 are the numbers that would be approaching 2. So you are first over here, you are 10 cents away, over here you are 1 cent away, and over here you are 1/10 cent away from $2. So it's clearly approaching 2 from the right. You have to practice a little bit these values if you have issues. So now you simply calculate these values. So it would be 1.9 squared. No coughing. And that number, I'm going to use the red numbers, is 3.61. And then you have your 1.99 squared, which is 3.9601. And then you have your 1.999 squared, and that is 3.996. So if you observe the trend of these numbers, the trend of these numbers is I'm getting closer to 4 all the time. So the red ones are saying I'm going to 4. On the other side, the blue ones, 2.1 squared, all the way at the end, is 4.41. 2.01 squared is 4.04. And then 2.001 squared is 4.004. So if you observe the trend going from the right, you see that the farmost one was 4.4 and then 4.0 and the 4.0, right? So from this side, it also goes to 4. Well, if it walks like a duck and quacks like a duck, it's a duck, right? So there you go. It's 4. So now you have visual representation and you have a chart. And technically you can do this with every limit that exists, as long as you can graph it and as long as you are willing to calculate things. So what's the rest of the chapter? Well, the rest of the chapter is actually to compute these limits using algebra and those kind of things, because we really don't want to do this chart. But you can actually call it quits on chapter 2 right now, because that's what it is. All right? You can call it quits because the same thing like you can call quits immediately on graphing. Immediately when you see that you can just pick whatever x's you want and you compute y's and then you connect the dots like coloring book, right? You learned that in 8th grade, hopefully. And you can literally call it a quits on learning anything else about graphing. Default functions and shifting and rotation and all of this, you can just know. You don't have to know any of that stuff. Because any function you ever get, you pick x values, you compute y's, dot, 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 connect, and you're done, right? But it takes a lot of effort to compute these things, especially when functions get to be a little bit crazy, right? So we learn all extra stuff to make it easier. Well, technically we are done with the entire chapter 2, right there, right? Because anytime you get stuck with the limit and you don't know what it is, well, limit goes to 3. Okay, what's happening? 3 points left of 3, 3 points right of 3. What's happening, right? You can compute and you can see it right there. But then we also want to find out other things in terms of calculations. So we have other sections to worry about as well. There are some key points to take from this lecture, and that is that there are these left and right approaches, which are actually called left and right limits. And combined, they make overall limit. So you have to define that. There's a big theorem that states the existence of non-existence of a limit. So we'll deal with that as well. So there are more things to cover in this section. But again, between the picture up there and the chart down there, we covered the entire chapter actually. So the limits are done on functions, and essentially they give us the y value of the function at the point you are approaching. We are not computing the point we are approaching ever. We are computing infinity of the points around it, and the infinity of the points around the point of interest will actually give us a trend and tell us what the y value is supposed to do. I want to also show now the other case where you have no limit, so that we can develop the theorem that we want. So you observe the function f of x equals 1 over x, and you draw the function. Again, from Precalculus, you memorized the shape, which looks this way. So you memorize the shape, and what we want to examine here is the limit 1 over x as x goes to 0. So that's what you want to examine. All right, fine. We know where 0 is at the origin, right? And we know that we can approach from the left, which would be going down this line on the left, which actually pushes us down the y-axis towards negative infinity. You know that the graph is never going to intersect y-axis because there is a vertical asymptote there, right? So as we approach from the left with the red, you get to go to negative infinity. And then you approach blue, right, from the right, and then that will go up the line, which would go up the y-axis, and you go to positive infinity. Do you see that they don't end up at the same point like earlier they did? So these two approaches diverge. I call this Romeo and Juliet approach. You have the blue for the boy and red for the girl, right? That's the stereotype that we all have to embrace. And then they either end up together or not, right? So, I mean, obviously, if Disney did the story, this would be it, and it would be all boring and like everything else. Luckily, they didn't, so that's the actual story. So, what we have here is that the answers that the left approach and the answer that the right approach, so the answers don't match. And we know that in the function, that's no bueno, right? Unique, right? Input gives us unique output. Well, this particular input of 0 gives us output of negative infinity and positive infinity at the same time. No, 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 right? So the limit does not exist. And that's what it means it does not exist. That the two approaches did not give us the same value. Now, it is very easy to see this using the chart of values, just like earlier. You are wondering what's happening at 0. You are going to approach it with 3 numbers, let's say, left and right. You can pick whatever. You like pain, use 17 numbers to the left and 17 numbers to the right. It's fine. So we're going to be first 10 cents away. Then we're going to be 1 cent away, then 1/10 of a cent away. On the other side, again, 10 cents away, and then 1 cent away, and then 1/10 of a cent away. And all you need to do now is to compute these values. Observe what happens. 1 over 0.01 is negative 10. Negative 100, negative 1,000. Which makes sense if you look at the graph, right? Oh, this was supposed to be red numbers. Give me a second. I need to make sure that I'm matching your notes, because your notes, you're using red, as I can see everyone, right? So this is your red approach. And the next number, right, would be negative 10,000, negative 100,000, negative million, negative, right, 10 million, and so on. You see that you are going with these guys to negative infinity. And the blue, all the way at the end, is 10, and then 100, and then 1,000, and there will be 10,000, 100,000, million, 10 million, 100 million, and so on. So these ones go to positive infinity. So now, what's the overall? Does not exist. That's the overall. Does not exist because they don't match. They don't converge to a single point. They don't agree. And we know we can't have that. So that's what we have here. Good. Morning. How are you?
Good.
Parking, right? Issue. I know. I know. Good. So, example 1, left and right approach, as we went from the left and from the right, collided at a single point. That point was the answer for limit. Example number 2, they did not go to the same point, therefore limit does not exist. There are other cases where you can claim the same thing. Now let's first write down one-sided limits. Let's do the purple. So we have the limit as x approaches a minus of f of x. Now that one can either be finite or one of the infinities. You cannot have does not exist on a one-sided limit. That makes no sense. One-sided limit, you always have to reach something, either a number or infinity. You can't have does not exist. So this is the left limit. Where you have to focus in your notation, you're focusing right here. You see that little minus sign on A? And then the second one is the limit x approaches a plus of f of x. Also can give you a finite value or positive, negative, infinity. This is the right limit. So you are focusing on, again, the minus and a plus. So if you have minus and a plus, those are one-sided limits. If you do not have minus and plus, those are the overall limits. Now, what is the meaning of this thing? Well, this is what I had as red, and this is what I had as blue. I did not introduce any new concepts, guys. All I did is I gave name to everything you see on this picture in red. I gave it a name as limit x approaches a minus. And everything you see on the picture in blue, I'm calling that now limit x approaches a plus. So if I go back, I would have to call this one limit of x squared as x approaches 2 minus. And we actually got 4 on it. And this one is the limit x approaches 2 plus of x squared, and I also got 4. So I didn't do anything new other than just give it a name of what we already hopefully understood from previous examples. It's just visual. You're approaching from the left. We'll call it the left limit. Put a minus on it, right? And call it a day. Again, over here, I have the limit of 1 over x as x approaches 0 minus is negative infinity. And the blue one, the Romeo, right? X goes to 0 plus of 1 over x is equal to positive infinity. So now those are the new names. Oh, come on. So now the major theorem on existence of limits. Says, if limit x approaches a minus of f of x is the same as the limit x approaches a plus of f of x is equal to L, then limit f of x as x approaches a in general is L. Otherwise, limit does not exist. This is major stuff. And the first time now in calculus, we have to stop a little bit and talk about housekeeping of the whole course. You are able to pass entire algebra course on with the skill monkey sees, monkey do. And that is, you see the way the problem is done, you mimic the same steps, you have the different number as the answer, right? Because you had different numbers to begin with, but it's all good. Precalculus, pretty much the same thing. You have to involve some concepts, but yeah. What you see in red is the way to do problems in calculus. If you don't know these theorems, and if you don't know what you're dealing with, you won't be able to do problems. And the issue with that in calculus is a statement like this, but particularly this thing over here, which is f of x, right? Some of you will probably try to do the homework this way. Okay, if f of x is e to the x, I do this and this and this. If f of x is sine x, then I do this and this and this and this. And if f of x is x squared, then I do this, 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 and this. Whew. And then you run into e to the x squared. Right? You cannot remember every possible combination, because under that f of x, you have whole spiel of functions, and then I have function composition. Do not try to learn this example by example, because you can't. If you go home and you just try to do homework right off the bat, it's going to take you a really long time to get through homework and a lot of frustration. You learn the concept. The concept was approach one-sided limit. I always have either a limit or infinity. I can deal with that. Then in that case, you don't care what f of x is, because you can compute point by point, if anything. Or you can draw the graph. So for the entirety of calculus, later on differential equations and everything else, our formulas now will going to have entire functions embedded in them. And learning it case by case is not going to be pretty at all. So you have to learn theorems. This part that you need the limit to exist is going to be central piece of further theorems. So if you can't do this piece, then everything else later, obviously you can do. Continuity, 2.6. We're probably going to get into continuity next week, but we might this week, depend on how fast we go today. So these are some concepts that you guys need to consider now. Learning definitions and theorems in this course is imperative. Understanding what they mean is imperative. Understanding that definition is what it is, and the theorem is which way we use it to compute. You will also see that certain problems in calculus are solved by writing a paragraph. You don't get to compute anything. You keep writing, right? So some problems are simply done by writing paragraphs. And you write a paragraph, maybe 3-4 sentences, and problem is solved, and you move on, and you didn't compute anything in terms of, oh, this is the way I did it in algebra and PreCalc. So some of those aspects will be there as well. And clearly you can't do anything of that if you don't understand these parts. Which is the reason why you should be stopping by the office hours. You should talk to your SI. Ali will be here eventually today to talk to you guys again. So, you know, keep working on these concepts, and keep learning theorems. Theorem is the way to do the problem. Yes.
So is this basically explaining that, like, even though a one-sided, there could be a limit, like the limit could exist, that doesn't always mean that the limit goes overall for both sides? Basically.
Yes. So what I'm going to do now is the example which is going to use this theorem directly to explain exactly what you said. Last time we touched upon the notion of the step function. So I'm going to draw a basic step function, 1 and let's say 3. So here we go. This is 7, not 6. So if you look at this function here, right? You look at this function. You can actually write the formula for it. it is constant function 1 when x is between 0 and 3, and then it's 3 when x is between 3 and 7. So you can actually write the function for it. And now my question is, what is the limit as x approaches 3 of f of x? Right? What is it? Doesn't exist. Right? Now, we actually have to use the theorem above to show that the limit does not exist. You have the left approach to 3, which is going over on the first line, and you will be using limit x approaches 3 minus, and you are approaching f of x, but that's technically 1. Actually, you know what I'm going to do? I'm going to write of f of x, but to the left f of x is 1, so I'm just going to rename it. Right? I'm going to plug in what f of x is, and then we see that we get 1 as the answer for y. And it's clearly a 1 because it's 1 across the board, right? It's 1, it's constant. The blue approach, approaching 3 from the right, is you going on the other line. That's going to be limit x approaches 3 plus of f of x. Now the plus side, well, that's this one. So that's limit x approaches function 3, which gives me 3. And this is where the theorem kicks in. Limit x approaches 3 minus of f of x is different than the limit of right approach, which implies that the overall limit of f of x does not exist as x approaches 3. So now you see in the notation 3 minus is the left one. We know the answer for that was 1. The 3 plus is the right one. The answer for that is 3. 1 is not the same as 3. Therefore, limit does not exist. Again, what's limit? It's the y value, right? Can you have the y value to be 1 and 3 at the same time and have a function? Hell no. You have to start connecting all of these dots at once to make sense of all of this, right? We know definition of a function. 1x unique y. Well, if x is 3, I get 1. If x is 3, I get 3. No bueno, right? Limit does not exist. So in a nutshell, limit is calculating y values. In this particular case, we have 2 different y values for the same x. Now, you might say, well, wait, x is different because this is 3 minus, this is 3 plus. No, no, no. This is still 3 and 3. The minus and plus are telling you about the infinity of the points. So this minus means we calculated infinitely many points to the left, and this plus says to the right, but still a 3 and a 3. 3 is a single location on x-axis. We know exactly where 3 is. And those minus and plus are not negative and positive. Those in notation that we have, that we adopted, that notation stands for infinity of calculations on the left side and infinity of calculations on the right side. That's all they represent. But you still have number 3 as x value. Cool? Everyone happy? Great. Now, a problem for you to enjoy. I just want to make sure that I did not. Good. So, these are the types of problems that are really valuable to consider. Like problem 7 in our textbook. So you have this thing, right? I'm going to draw this in the notes. And the more you sit and analyze and stare at problems like this, the better off you're going to be later on in all of calculus. It's just analysis, analysis, analysis. All right, so 1, 2, 3. I need 3, 2 open circle this way, 4, 1 open circle this way, and then something that looks quadratic after that, doesn't matter. They just call this h of x. You do not get any functions explicitly, even though you can write it as a piecewise function, no one cares, right? So here are questions that we are going to consider here. So this is, let me just give you the scale over here. So 1, 2, 3. It's supposed to be quadratic piece going, curving up. All right. So from your previous life of pre-calc, you immediately see that you have a maximum and a minimum and increasing and decreasing, all of those cool features. Digging deeper, you might know this is a piecewise function that has a linear line x plus 1 from 0 to 2, and you have another linear line that will be negative x plus 4, no, plus negative x plus 5 from 2 to 4. Then you have a parabola, right, with the vertex at 4, 1, so you can write that as well. So you have all of these features, right? We don't care about any of them. We don't need them at all. All I need here is analysis about where I have and where I don't have a limit. And if I carefully consider all of the points, right, I see that in this particular case, limit exists everywhere. Which means that I can compute all of the y values using limit. Now look at this. Pick any point. Pick point at 0, 0, 1. I can use the right limit to compute that the limit is 1. There is nothing from the left, so that's it. So I can use, let's go with green. Over here, I can say limit x approaches 0 plus of whatever h of x is, I don't care, is clearly 1. It's clearly 1 because that's the y value that I see on the graph. End of story. Right? Then I have the limit, let's say, x approaches 2 of h of x. What is that? Well, to compute the limit at 2, I have to approach 2 from left and from right. Well, that means I'm going to do, right, the Romeo and Juliet approach over here. I'm going to go this way, and I'm going to go this way. Okay, let's see what Juliet is doing here. So limit x approaches 2 minus of h of x, and that's going to give me 3. And a Romeo plus, right? So from the right is also giving me 3. We just had a theorem that says when left and right approach have the same value, overall approach is that value. Therefore, the limit is 3. Before you scream, but there is no point there. Exactly. There is no point there. This is the reason why limit is so damn powerful. You don't even need the point. We computed infinity of the red points to the left and infinity of the right points, the blue, and all of them were screaming 3. So the answer is 3. End of story. Same thing is going to happen at 4. What is the limit of h of x as x approaches 4? Right, what is it? Well, again, approach red, and that limit as x approaches 4 minus is what? 1. Blue approach from the right is what? Overall limit is what? Again, left limit and right limit agree. They are at the same point. Therefore, we get that.
But it's gonna be 4 if you approach it from the left, but it doesn't say where it starts, right?
What?
If you start at 0, then the limit's gonna be at 3.
What do you mean?
If you come all the way from the x, from the 0.
But we are approaching 4. Why would be 3? The value of the 4 is 1.
Yeah, you're approaching 4, but it doesn't say where it begins. Where do you start approaching it from? That's what I mean.
You start approaching it close. It's in the neighborhood, right? But even if you started approaching it at 0, it still doesn't matter. It's still going to be the same answer. It's still going to be the same answer, because you only care what's happening in the neighborhood of the point that you are looking at, right? Because you are technically computing the value of that point. And now I have an interesting problem, which is where precalculus and calculus are going to disagree, and you guys will have to make a piece with what you you will have to take the answer in terms of, okay, this is what I need, so I'm taking that as the answer. So here's the graph of f of x, and you have this point 3 over here. That's a bad value. I don't want to have everything to be 3's. So let's do it this way. All right, so you have a linear line. That's 3. That's 5. And that's 1. So this is another one of those pre-calc versus calc. What is the limit as x approaches 5 of f of x? Three. Very good. 3. We approach 5 from the left. You are approaching this non-existent point, the open circle. You are approaching 3 on the y-axis. Romeo, approach from the right, goes down the line, goes down the y-axis, and both Romeo and Juliet agree that location for them to meet is 3, right? So the limit is 3. End of discussion. What's the function value that the precalculus tells us? 1. Right? Be very careful about this. So you see that the limit computes the y value. But see, what limit cannot compute is if you have a single point in space that is dislocated like that. Remember that limit deals with every other point but that one. limit cannot detect. Limit cannot detect that one. There's nothing you can do. So precalculus will return that as the answer. Precalculus will say f of 5 is 1. And precalc can detect anything else other than that 1, because precalc is 1 point at a time, right? Now, if you are to go with the precalc and say, okay, what's happening at 5.1, what's happening at 5.2, right? You will quickly see that there was something odd, right? If you compute a whole bunch of points before and after 5, precalculus would give you some kind of a picture that would look like this, like, okay, and then, okay, like that, and then 1 point here. So if you compute this with the precalculus and you do a lot of these calculations, you will come up with this, right? And then you would see that something is up, right? Something is weird. Now, calculus is able to detect that immediately, but a calculus is not able to detect this. So that's something that you need to be careful about. Good. And I think that's it. I hope you are not disappointed. That's what we have for limits. You can quickly take a look at the problem 22. If I'm going to put a problem like this on a test, it's going to be 22. Perfect. It has limits and non-limits and like all of this stuff. Look at it. Amazing. All it's missing is a dislocated point. You have the limit at 0 is 0. Does not exist here, does not exist here. This just perfectly exists here or any other point, right? So you can really have a good practice with this problem. Those of you who want to take a look at a little bit more advanced stuff, take a look at this problem. Right? That's something that you would plug in Mathematica when you download it and try to make sense out of it. Right? All of the problems that have a blue T next to it in the textbook, it says technology. So technology will aid you in terms of understanding. It's not easy to understand that problem there. That's why I said, again, this is not an honors option of the class, but still, some of you might like to take a look at some more advanced exercises. I'm expecting 100% of the students in this classroom to know this like a palm of their hand, this problem. That should be zero effort for anyone, because that's what 2.2 is across, and be able to answer all of those 9 questions up there, looking at the graph. And I believe the next one is pretty much the same. Yeah, look at these. I should just copy and paste one of these. That's technically what it is. That's perfect. Limit is 2, function value is 3, limit does not exist, function value is 2, limit exists, and function value, and all of them are the same at that point. This is perfect. These 3 problems, amazing. And yeah, that's it. So we'll restart for the next lecture.